our vibration system, and accelerator that could be a motor, okay, and amplifier that could be op amp. So basically here I'm listing out in this diagram is in every single block here that always have a way to formulate into mathematical representation. So that means eventually once you starting from this conceptual schematic diagram, then you're working into individual subsystems and develop the mathematical models for each system, and then from there you begin to do Laplace transform, etc., to convert everything into the S domain. So basically, this will be the block diagram. Really have something you can work on. Then you can find out the output to input, which means the transfer function of the whole. Okay, and this is the the fundamental units for using the block diagram. So for example here for this case, and like we did before, x3 equal to g2 multiply x2 in turn equal to g1 times x1. So therefore x3 equal to g2 times g1. So that is the combined equivalent diagrams. And for writing this, we see this is an algebraic multiplication. So basically, in writing the block diagram, the orders of these things is not important. That won't change the ratio of x3 to x1. We always concern is the transfer function. So really, the change in the order really doesn't matter. And now for this case, we can see x3 equal to g times this. Let me get this out. So say now let me take at this point is equal to 8 the arrows. So by reading these informations, x3 equal to g times e, okay. And what is e? E equal to x1 plus or minus x2. So that is the information. And the equivalent model will look at this one. So basically from here you can see x3 will be equal to summation of the two signals, this one, and equal to g times x1. And this one basically is g times x2. Okay, so from here you can see x3 equal to this. So basically the two systems are equivalent. Okay, and for this one basically here, for example, x2 is equal to g times x1. And then for this case, I think this is the same thing. And so g equal to x2 equal to g times x1. And at this point, on the same thing here, the x2, if you look at here, g times this point, at this point is x1. So g x2 here at this point, x2 equal to also g times x1. Okay. So basically, this signal from here is we take the feedback to somewhere, and the feedback is based on x2. So for these equivalent systems, if you like to take the feedback from rather than from here, instead from here, then basically if you want to make the two things equivalent, then you have to consider a block here and to make the signal equivalent. Okay. And the learning point in this slide, given the original diagram or we find out the equivalent diagrams, the learning point in this slide is just to tell you for a single system, there's so many configurations of the block diagram you might be able to use. So don't worry if you kind of work with a team or in the group, and your thinking might lead into a block diagram that could be different from your team members. That's okay. Okay, and the point is to compare the transfer functions. As long as the transfer functions the same, basically you and your team members are on the same page. Okay. So that is the one for this. And we might have other exercise. So this is very trivial. So we might they continue to look at more practical systems here. Okay, so here we try to use block diagram to represent the typical control systems. And here I'm going to introduce the a method, the control system, which have the controllers, P control, I control, the proportional controller, integral controllers, and PI controller, PD controllers, and PID controllers. And these will be the very quick introductions here. And some of the figures we might have seen in the introductions. So this is the on-off and control, okay? And on-off, this is off, this is on. So basically here, our decisions of the things depends on the errors, okay? And for example, once the error, for example, look at this system. If the water has been full, then we turn it off. The water choose the level 2 load, we turn it on. And how to evaluate the signal, basically here we're using our bare eyes to regulate the water level, and that information serves as the rule here. Okay, basically depends on the signal we controllers, our brain determine to turn off or on. This is a very primitive system. This is the proportional controller. Proportional controller, that means basically the controller is a constant gain. The constant gain, for example, K, and here the K is a constant. Okay, so that is called the P control or proportional control. Okay, so here, I don't know, for the printing purpose, I think there's a, yeah, okay, so for example, the output in the time domain equal to K times E, so written by this. So again, for this control, K is constant. And the same thing, I'm going to take something here. The second type is the integral control. And so here we have an integral control, basically the Ki is this one. So Ki is a constant, and multiply the integral of the signal over time. So here is the E of t. Okay, so for this one here, this is our U of t. So U of t equal to Ki, the constant, the I constant, multiplied with the integral of the E over time. Okay, and so for this case, if we take the plot transform of this equation, basically that is a U of S equal to Ki. And again, if you remember, the integral we put into transform, the Laplace transform basically is S and E over S. Okay, so basically here we come up with is this one, divide, we move the E to here, so the transfer function between U and E equal to this one. So this is the integral controllers, I over S. Okay, compared to the previous page, the controller block functions, the block functions for controller for previous page is simply constant here. Okay. This is called the PID controllers. So for this case, you can see this one. From here, let me rewrite here. So basically US and divide by ES and equal to, given this one, let me rewrite here. So that is the TI and KP and plus KP EIS plus KP TI TD squared. And let me do this one, let me put it to the term by term. So basically that one is equal to KP TI. One over S. And then the second term is simply KP. The third term is KP and TDS. Okay. So after this, then you can see the second term is we call the P controller. The first term, looking at compared to the previous page, basically this term corresponding is we call the integral controllers. Okay. And the third term is new, and that the additional new terms here. So that is because due to multiplication of the s in the Laplace transform, if we have any derivative of any functions, the Laplace transform is s times f of s and minus f0. Assuming we don't consider initial conditions, basically derivative of functions basically equivalent to the Laplace transform is s multiplied something. So due to the existence of this s, that is the we call the derivative control. The derivative controller, that means D control. Okay, so that means in this single term that composed of the PID controllers. Okay. Will that be too quick? I move to slide be too quick for people to take notes. If you need more time, give me a signal. Okay. Good. Okay. So we can look at this. We can exercise this one, and here it goes complete in the printing. I don't know why. Okay. So here we want to derive the transfer functions, and for this particular systems, we have one output C. And we have two kinds of the input. One is this one, and that is R. So that is our command input. But we also have a particular, the second one, that is another input, they call it disturbance. Disturbance, that means the perturbations of the nominal systems, and due to, for example, frictions, or due to the portion you have not modeled yet. Okay, so everything can be classified as the disturbance. And this is the closed loop, feedback closed loop systems. And we have three blocks, and G1, G2, and H. So here we can exercise how to write the transfer functions between C over R. And then we also want to find C over D. Okay, so that is the transfer function we'll try to formulate. So based upon this one, you can see here for C over R, so to find out this one, basically once you want to find that one, you can assume D equal to 0 simply because these are linear systems. So you can always decompose an individual influence and then superpose together. Okay, so for this case, we're assuming D equal to 0. So by reading this, so from here we can work on the graphically. C equal to G2, multiply the signal here. Okay. When D equal to 0, basically the signal at this point equal to here. Okay. So now we multiply that signal, and that signal here at this point is G1. Multiply with, let me call this is E. And what is E? E actually equal to R minus this one, right? And what is this one? This one is equal to H times C. Very good. So we'll kind of tier-wise propagate the information from the output and to the input. Very good?
Can you repeat this one?
Yes, let me do that again. So let me write up the signal here. So let me say this is the signal A, this is signal B, this is E, and then we call the signal, let me call using different, this is called the alpha, beta, and here the point is gamma. Okay. So from here you can see, and C equal to G2 times alpha, right? And here the alpha equal to beta. And beta equal to G1 times E. Right? And then what is E? And E basically is equal to R minus gamma. And what is gamma? Gamma equal to, gamma is the output of this one, so that is H multiplied with this one, this is C. Okay, so simply we plug in everything, so therefore what we introduce, and that one we introduce, that is G2, and gamma, alpha replaced by beta, and beta equal to G1 times E, and then you G2, G1, and what is E? Equal to R minus gamma, gamma is HC. So basically it becomes like this. Yes?
Why is alpha equal to beta, not beta plus D?
Yeah, because here when we are concerned about the C over R, then we assume this one equal to 0. Okay. And on the other side, at this moment, if you want to complete by not assuming D equal to 0, so basically here you try to include the inference of D as well, then at this moment, alpha must be replaced by here. Let me write it out completely. So by including D, then D should be added up here. Right? So assuming D is not equal to 0, then we're putting D here. Okay, so that means that will be, in this way, we need to modify. Let me rewrite again. So here, including D, let me write up here. So basically here, if we include in the inference of D, that is G2 times alpha equal to D plus beta. Let me use the same color. Okay. So then beta, what is beta? So G2 times, and let me write up D later on. Beta equal to G times E, E1, and, okay, let me write. And then this one. And G1 times E, and G1 times E equal to R minus H times C. You good? Okay, so complete description is equal to this. So basically this is C, okay, equal to this one. So based upon this, we can do the simplifications. So this is a complete description of the system. Let me work on this one to here. So let me multiply the right hand side. That is G2 times D plus G2, G1, and G2. Here is a G1. G2, G1 times R plus minus G2, G1, and HC. Okay? So after I simplify this equation, the right hand side of this equation becomes this. Then I begin to do something here. So so from here there's a 2C. So here let me move the C from here. So 1 plus G2, G1, H will be equal to G2D plus G2, G1R. Okay, so therefore from here, because here we have 2C on that side, I just combine them together. So from here then I divide both sides by this one, 1 plus G, 2, G1, H, G2D, and I simply divide both sides by this, okay? And 1 plus G2, G1, H, G2, G1R. Be good? Okay, so now you can see, so therefore, you see the output is, the contribution to the output from two things is from D, one is from R. there's a two kinds of the input. So therefore, the transfer function C over R simply is this term. This term representing is the transfer function of C over R. And the C over D simply is the first term. So that is the answers here. Okay. So any other questions about this? So I think I agree with Scott. Maybe the better way is we just try to start from here. We just try to include everything in a single step, and then we'll come up to that. Okay, it's good. Okay, then we can move on to the next slide. So for this one, again, we have seen this system, and this is a simple RC circuit, and that is the governing equations and happened in the modeling step before. And so for this case, we will be able to come up with the block diagrams. So from here, you can see the current. And we might be able to look at here the informations for these systems. And you can see this system, basically I equal to comparisons of the output terminal to input terminal, and then multiply with a constant gain 1 over R. So again, we work on this one. So in terms of the block diagram, from these equations, you can see I is our model-wise, the modeling in the model in terms of the I is our output in the block diagram. I equal to a constant 1 over R multiplied with a difference between two numbers. So the difference between two numbers, EI and EO. So this equation we'll come up with is this one. Be good? Okay. And also by including these informations, then you can see this one, the Laplace transform of this equation is EO equal to C, and again integral corresponding to this one. Okay, so EO equal to IS multiplied with CS. So right now we have IS here. We simply copy this one into here. Okay, so this portion. And then from this equation, IS multiplied with CS equal to EO. So with the simple equations, we can complete the entire block diagrams. Good? Okay, so basically this is a block diagram for these systems. And this is a simple RC circuit. Basically here you can see it did have the feedback loop. And we call the unitary feedback system. And the output is regulated and through this way, and eventually the output will be eventually equal to EI, okay, in this system in steady state. So this is another typical example here. In particular, this page, in this kind of sequence, we learned how to start from the individual mathematical modeling piece by piece to make up the complete control system, the block diagram systems. Okay. In the meantime, some people completing the notes. I forgot to bring the handouts. Once the day we hit there, I will go back to the department office. I make a copy of the signal flow graph, and that's the next section. And hopefully we can finish everything for you to complete homework which is due Monday, right? So hopefully I can complete all the necessary information by Friday. Then per our schedule, and Wednesday next week, we're supposed to have a test one. So test one will cover everything up to your completion of the homework 2, all the things, topics involved. Okay, so now it's this one. Okay, now for this system, we can exercise. So now this is our original systems, and we want to derive the transfer function of these systems. Then we see how can we do it. So starting from here, and basically here we have 3 blocks, and here is the feedback, and here somehow we call the feed forward. So this portion is called the feed forward loop. Okay, because it's the feed the signal forward to somewhere, and this portion is called the feedback. Okay, so basically this is the combination of the 2 loops. And now we can, whatever the loops, we work on the algebra. So from here, C equal to the summation of the 2 signal, 1 is here, 1 is here. Okay, so let me dig out here and here. And we start from here first. So basically, this one equal to this gain multiplied with whatever here. So let me label it and say, let me call this is alpha. Okay, so basically from here you can see C equal to alpha, this one, plus this one, what that one equal to H1 divided by G times alpha. Right? So C equal to the 2, information converged to there, and this one equal to this one multiplied with alpha, because alpha equivalent to everywhere in this here. Okay. And now what is alpha? And so basically here is 1 plus H1G. And multiply, right now I'm working on alpha. So what is alpha? So these terms. So this will be alpha. So alpha will be equal to, say this is the signal E, and alpha will be equal to G times E, right? Alpha equal to G times E. And what is E? E equal to R, the difference between R and that one. So R minus, and what is this? That one is H2 multiplied with this one, right? And that one is alpha. So that is H2 times alpha. Okay, so somehow here, you can see, I want to get rid of the alpha, but somehow here alpha appear again, right? So we have to work on the alpha first. So here the whole terms, let me work on the other side. The whole term alpha equal to this one, GR minus H2 alpha. Okay, so maybe in this way we can find out the relation between alpha and G. So let me do it. So here that is alpha times 1 plus G H2. I simply turned out the right hand side and combine the alpha term to the left hand side equal to GR. So therefore alpha equal to G 1 plus G H2 times R. Are we okay? So now we continue. So since we already figured out the alpha here, so for this case here we have the alpha information. I'm going to replace alpha by this term here. Okay, so so right now let me write that 1 plus H1G times G times R minus and H2 and alpha I'm going to replace by the term here we come up with, and that is G 1 plus G H2 times R. You good? Okay, so now we can simplify. Let me do this one.
Question.
Yes.
Why would you replace the alpha there when in the very first line?
This one?
No, up one.
This one?
No. To the left.
This one?
Yeah.
Okay.
Why couldn't you just replace that alpha? Why'd you replace it with the second equation?
Yes, you could. And for example, here you can replace alpha in terms of C. Is that what you're saying?
Yeah, it's like you.
Yeah. So.
Never mind.
Okay. So let me do this one. So you're saying that from this equation, C equal to 1 plus H1G times alpha, right? So again, yeah, if you could, yeah, of course, if you like, you can also replace alpha in terms of C. So that means alpha equal to C 1 plus H1G. Yeah, so if you like to replace alpha in terms of C, you can get in here. For this relation, we have the relation alpha in terms of R. So if calculation, I think this is a good one, good idea. So if your calculation is correct, then it doesn't matter which way you do the replacement, result will be the same. Result will be the same. Okay. So we do this one first, and let me simplify this. So now I simply multiply G into the first one, that is G times H1. Then for the second one, and that is the function of R, and then let me do this one. So 1 plus G HQ, and this is 1 plus G HQ minus H2G. Okay, I simply do the algebra. I turn 1R out, so that's becoming 1 minus this one, and I arrange the result. So from here, these two terms can be cancelled. Okay. So therefore, from here we continue, right? So that is G plus H1, 1 plus G HQ times R. So therefore, you can see the output to input equal to these simplified expressions, and that one equal to this. Okay. And we might try these suggestions to see what happened. So for this one, let me do that one. Let me rewrite the other one. So I don't want to do it. I know that will be a little bit more complicated. Sorry. But you know, everyone knows the ideas. Okay, you can give it a try. And this is the third approach. I would say if this is our first approach, and this is our second approach suggested by you. What's your name?
Sam.
Sam? Good. Very good. And this is the third method suggested by our textbook. And the procedure is this. In our textbook, the trying is be honest with you, I don't know how they come up with this one at this moment.
I think
Yes.
it's just if you replace the whole block in there. No, up one.
Up one?
No, the equation you have.
Okay,
This,
this
that one, if you just replace the whole block with the equation you found, right?
this one,
Yeah.
and come to this one.
Yeah.
Okay, John, I know John. So everyone knows John's saying. It's
So
saying replace alpha with
no,
this.
the whole block, because you said the whole block, like the whole. You have the underline there, that's alpha, right?
Yeah, where you have the alpha with the bracket. Instead of replacing that interior alpha, you can replace that whole outside alpha with that one equation.
And that comes up with that.
Everyone get it?
Yeah.
I didn't get it. If I don't get it, I will pass. I will move on. Okay, good. Okay, so seems they shouldn't have any questions about these slides. Good. Okay. Then you might continue to exercise for this. This will be first.